Hello everyone, myself Mrs. Janvi Darshan Raut, lecturer in Electronics and Telecommunication Department of Pravin Patel College of Diploma Engineering and Technology. In this video, we are going to study about our new subject, that is emerging trends in electronics. Okay, the subject code for emerging trends in electronics is 22636 and the short form is ETE. Okay, now in this emerging trends, every technological area is developing at an exponential rate. New applications are coming up, and it is mandatory for all the technologists to be well versed in these developments to survive and provide satisfactory and quality service to the society and the industry. This course aims to prepare the diploma graduates to be conversant with such emerging trends. The main areas in which such developments are encompass smart system, digital factory, and communication. Okay, in this subject, the students having only the theory paper of 90 minutes of and it is of 70 marks. The exam to be conducted in the online form only. Okay, now let's turn on to our unit. So our first unit, that is unit 1, is advanced processors. So we will start with this. The learning outcomes for from these videos are the advances in processor architecture, risk processor, pipelining, superscalar concept, advantages, disadvantages, and applications. So firstly, we will start with the introduction. Okay, in the advanced processors, risk, pipelining, superscalar concept, and advantages and disadvantages are described in this video. The processors have undergone a tremendous evolution throughout their history. Key milestone in this evolution was the introduction of the microprocessor, term that refers to a processor that is implemented in a single chip. The first microprocessor was introduced by Intel under the name of Intel 4004 in 1971. It contained about 2300 transistors, was clocked at 740 kHz, and delivered 92,000 instructions per second while dissipating around zero point 0.5 watts. Since then, practically every year we have witnessed the launch of new microprocessors delivering significant performance improvements over previous ones. Some studies have estimated this growth to be exponential in the order of about 50% per year, which results in a cumulative growth of over 3 orders of magnitude in a time span of 2 decades. This improvement have been fueled by the advances in the manufacturing process and the innovation processors architecture. The complexity of an integrated circuit is bounded by physical limitations on the number of transistors that can be put onto one chip, the number of package terminations that can connect a processor to the other parts of the system, the number of interconnections it is possible to make on the chip, and the heat that the chip can dissipate. Advancing technologies makes more complex, powerful chips available to manufacture. Processor selection criteria. With numerous kinds of processors, various designs are available for digital systems. Following considerations need to be factored during processor selection for a digital system. First, that is performance of consideration, power dissipations, power considerations, memory, peripherals, operating voltage, specialized processing units, and last one is the price. So firstly we will start with the performance. The first and the foremost consideration in selecting the processor is its performance. The performance speed of a processor is dependent primarily on its architecture and its silicon design. Evaluation of fabrication technique help packaging more transistor in same area, thereby reducing the propagation delay. Also, presence of catch reduces instructions data fetching time. The pipelining and superscalar architectures further improves the performance of processor. Branch prediction, branch branch prediction are some other techniques used for improving the execution rate. Multi-cores are the new direction in improving the performance. Rather than simply stating the clock frequency of processor which has limited significance to its processing power. Next is power. Increasing the logic density and clock speed has adverse impact on the power requirement of the processor. A higher clock implies faster charge and discharge cycle leading to more power consumption. More logic leads to higher power density, thereby making the heat dissipation difficult. Further, with more emphasis on greener technologies and many systems becoming battery operated, it is important the design is for optimal power usage. Techniques like frequency scaling, reducing the clock frequency of processor depending on the load, voltage scaling, varying the voltage based on load can help in achieving lower power usage. Further, asymmetric multiprocessors under near idle conditions can effectively power off the more powerful core and load the less powerful core for performing the task. SoC system on chip comes with the advanced power gating techniques that can shut down clocks and power to unused modules. Memory. Usually designers make the decision to use internal or external memory after they define the required amount of code, space and data memory. Internal memory is typically the most cost effective memory type, but it is also the least flexible. For this reason, designers must determine future growth possibilities and whether there is an upgrade path to microcontrollers with large code space. Next is peripheral set. Every system design needs, apart from the processors, many other peripherals for input and output operations. Since in an embedded system, almost all the processors used are system on chips. It is better if the necessary peripherals are available in the chip itself. Operating voltage. Each and every processor will have its own operating voltage conditions. The operating voltage maximum and minimum rating will be provided in the respective datasheet or the user manual. While higher end processors typically operated with 2 to 5 voltage rating, including 1.8 volt for cores and 3.3 volt for IO lines, needs specialized devices. It is deciding factor in low end microcontrollers based on the input voltage. Specialized processing unit. Apart from the core, presence of various coprocessors and specialized processing units can help achieving necessary processing performance. Coprocessors execute the instructions fetched by the primary processors, thereby reducing the load on the primary. Floating point coprocessor. RISC core supports primarily integer only instruction sets. Hence, presence of FP floating point coprocessor can be very helpful in application involving complex mathematical operations.